Welcome everybody to Algebra 2. We've got section 3.2 today on complex numbers. All right, as we've done before in the past with these introduction slides, what I'd like you to do is take a second and pause the video. Here we're trying to determine which subsets of the set of complex numbers contain each given number. So I'd like you to pause the video and see if you can't make some predictions on which of those 6 numbers given at the left belong to which subsets of this set of complex numbers. So pause the video and I'll check back in a few seconds to go through this. Okay, well, let's have a look. Problem number 1, or number 1, we've got the square root of 9, which is equal to 3 or negative 3. We've got integers here, and integers, the positive 3 would fall in the whole numbers category, and the negative 3 would fall in the integer category. Remember, natural numbers, that's where, actually this is a very neat talk to have, and I won't take much of your time to do this, but this is kind of the progression of how we developed our numbers to explain the world around us. So, cavemen counting rocks, they started off by the natural numbers, what we use to count, numbers like 1, 2, 3, I have 5 rocks, Then whole numbers were introduced to include 0. We needed something to represent no rocks. So if I have 3 rocks and you take away those 3 rocks, then I have 0 rocks. Next, as our number system progressed, we developed integers, and this includes negative numbers. So now tax collectors would come around and say, oh, you owe me three gold pieces, 3 doubloons or something, and you'd say, I don't have that. And then if you have 2 doubloons, then you know that that tax collector is still expecting 1, so you technically have negative 1 doubloons or whatever. After that, rational numbers were established. These are your fractions, and we use these to describe, obviously, parts of a whole piece. So, I have half a rock, or, my land is 1/2 of your land, something like that. Rational numbers include those fractions to break apart numbers using division, divide them up. Okay, all of this got grouped under the classification of real numbers, numbers that we can work with and see and evaluate. We also include irrational numbers here. These are numbers like e and pi that were used in, or like square root of 7. A lot of these emerged from geometric observations in like ancient Greece. So they're still real numbers, but they are very intricate. They are not decimals that stop. They can't be expressed as a fraction. Well, what we found that there were situations where we would need imaginary numbers to kind of fit a need. So we saw the situation where we had a parabola that did not intersect the x-axis. That actually has solutions, even though we called solutions x-intercepts. Imaginary numbers kind of fit that need to give every single parabola 2 solutions. And that's something we'll explore further in later chapters. But we needed this set of numbers to kind of establish an ironclad pattern for us. And you can see that imaginary numbers use this variable I to denote a negative underneath the square root. All right, and then all of this falls under the blanket of complex numbers. So our entire set of numbers are complex. All right, let's look at number 2, the square root of 0. Well, that equals 0, and that falls into our whole number category. We have no rocks. Number 3, the negative square root of 4. Well, that's negative 2, and that is an integer. Number 4, the square root of 4/9. Remember, if we take the square root of a fraction, it's like square rooting the top and square rooting the bottom. We've got 2/3. That's a fraction. That falls in our rational number set. The square root of 2, that is a decimal that keeps on going. 1.41, da 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 da. It does not stop. That is an irrational number. Drove the ancient Greeks mad. And then lastly, we have the square root of -1. Well, that's kind of a dead giveaway. The imaginary unit is defined as the square root of -1, so that is an imaginary number. This slide, really this introduction, was designed primarily just to give us an understanding of vocabulary and classifying all these different types of numbers that exist in our mathematical system. All right, so now that we're talking about complex numbers, how do we classify all these numbers under the same blanket, no matter what subset they fall into? Well, our solutions, and really all of the complex numbers, follow this form, a plus or minus bi. So it looks kind of like an expression instead of an actual number, but it really is a number. And so we want to remember to think of it that way. That is simply representing a number, even though we see some variables in there. All right, there is a real component to that, a, and an imaginary part, b. So you can see that the real part has no I attached to it, while the imaginary part does have I attached to it. And remember that I is just a placeholder for square rooting a negative. All right, and if we square both sides of that little definition, we get I squared equals -1. All right, and again, we already talked about having this complete set of numbers allows us to find the solutions to all quadratic equations, even ones that don't have x-intercepts. All right, how to simplify negative square roots. If we don't see an I present, but we do have a negative underneath the square root, we know how to handle that now. If r is a positive real number, then the square root of -r is equal to the square root of -1 times the square root of r. This is called the product property of radicals. If I have two numbers multiplied underneath a square root, then I can separate that and refer to it as the product of two square roots. So that's what we've done here in this first step. And then by definition, the square root of -1 is I. So we use that I variable to denote that that's an imaginary part to a number. All right, so the different complex numbers, well, if we have b equaling 0, that means there is no imaginary part. So it's all a real number. And here they've given us some examples of real numbers. If a equals 0 and b does not equal 0, we have what are called pure imaginary numbers. Now there is no real part. Everything is imaginary. So these numbers simply look like something I. And then lastly, just a typical imaginary number is one that has a real part and an imaginary part. But again, these are just numbers. Even though they look like expressions, they are just numbers. All right, so now that we've expanded our number system, let's use it. Number 6, here we've got the square root of -64. I don't like that negative sign underneath the square root, so I'm going to refer to that as the square root of -1 times the square root of 64. And the square root of -1 is I, and the square root of 64 is 8. Now notice we're not square rooting both sides as a means of problem solving. This means the positive square root of 64. So actually my introduction, I should not have said plus or minus 3 for square root of 9. It should have just been a positive 3. If anybody caught that, good for you. Okay, so simplified imaginary number 8i. For number 12, same concept, except now there's a 6 multiplied out front. We just need to hang on to that. So I got 6 times the square root of -1 times the square root of 63. Okay, so I've got 6i times, and I just want to see if I can clean this up at all. So you may remember doing factor trees, where we try and break down a number through multiplication. 63 is 9 times 7, and 9 can break down into 3 times 3. So now at the end of the branches of our factor tree, we've got a pair of 3's and a lone 7. And what this is saying, and I think a lot of teachers just say, oh, if there's a pair, then move that out front, and if there's not a pair, then leave it underneath. Well, why? Why does that make sense? So just a quick explanation here. Underneath, we've got 3 times 3 times 7. So what we've really done through our factor tree is set up 3 times 3, that's 3 squared, times 7. And remember, multiplication under a radical can be split up. So this first part is the square root of 3 squared. Oh, that's just 3. The square root and the square cancel out. That doesn't happen with this, the 7. So you can see why we look for pairs to free, but if it doesn't have a pair, then it stays underneath. All right, so we've got 6i times 3 root 7. And again, think about what this means. 6 times I times 3 times root 7. We can clean that up. The 6 times 3 will be 18 times I times root 7. Now, I know what you're thinking. Why is the I in front of the square root? Well, it's just so we don't confuse that as being underneath the square root. So if we have an imaginary number that has a square root in it as well, we typically write the I out in front of that square root. So there you have it. Quite a bit of information in that slide. I hope that makes some things clear that maybe weren't before. Our second example, find the values of x and y that satisfy the equation. So here we've got this imaginary number which equals, or complex number, which equals this complex number. Well, if the two numbers are going to be equal, that means their real part has to match and their imaginary part has to match. So to find x, I'm just saying, hey, I want this 3x to equal 27. What must x equal? So if I want 3x to equal 27, x has to be 9. And the same thing with the imaginary part here. We want positive 6i to equal positive yi iota. Well, if that's going to be true, y has to equal 6. And that was pretty easy to spot. Let's try the next one. Okay, our real part, 1/2 x, has to equal the real part in the other number. So multiply both sides by 2, x has to equal 30. And in the imaginary part, negative 3y, that has to equal positive 2, right, to make the coefficient on the I term match up. So y equals negative 2/3 when we divide both sides by negative 3. So really simple once we get it set up. You could say that for a lot of mathematics, but really just kind of solidifying the idea that these are numbers, so they have to match perfectly. All right, working with imaginary numbers. Now, again, this is kind of reinforcing the idea that imaginary numbers or complex numbers, they are numbers. So for 22, we're taking a number plus another number, one number plus another number. We should get a new number, right? We shouldn't end up with some fancy expression or anything like that. We should get another complex number. Well, all we do are combine like terms. We can treat I like a variable here, even though it represents square root negative 1. That property holds, so we can treat it as a variable throughout the whole process. So if we are just adding or subtracting, it's a matter of combining like terms. So I've got a real part of 9 plus another real part of 11. That's a real part of 20. I've got positive 5i for my first imaginary part, positive 2i for the second imaginary part. If I combine those together, I get 7i. For 26, the process stays the same for subtraction, except now, just as if these were expressions, we distribute that negative, minus 2 plus 9i. So 16 and negative 2 is 14 for the real part. Negative 9i and positive 9i gives me plus 0i for the imaginary part. Oh, that is a nice, clean 14. I can box up that other solution. 28, here again, more distribution. It's just following order of operations. So I've got minus 2 plus 3i when I distribute that negative. Let's combine the real parts. 16 and negative 2 is 14. Positive 3i minus I is plus 2i for the imaginary part. Now, it looks like we could factor out a 2 or something like that. You do not need to do that. This is a number, and that is our final answer. We don't want to distort that at all. So just leave it as it is. Oh boy. Example 4, the literature lesson here. And this is a good example. Often you will see word problems in math that look incredibly intimidating. Don't be intimidated by the words. So much of this is just fluff, and they really talk us through the process here. So take the time and read it carefully. It's a good lesson for all word problems. I know a lot of students will look at this and just say nope and shut their textbook. Don't be that person. To invest a little bit of time, read the problem, and give an honest attempt at it, because if we can interpret this and come up with a reasonable means of solution, we're going to keep growing and becoming a better math student. All right, here we go. Electrical circuit components such as resistors, inductors, and capacitors. We do not need to know anything about electrical circuitry here. We're not electrical engineers. They're just explaining this concept. This opposition is called resistance for resistors and reactance for inductors and capacitors. Each of these quantities is measured in ohms. The symbol for ohms is the uppercase Greek letter omega. The table shows the relationship between a component's resistance or reactance and its contribution to impedance. A series circuit is also shown with the resistance or reactance of each component labeled. The impedance for a series circuit is the sum, there's our first math word of the whole process, of the impedances for the individual components. Find the impedance of the circuit. So really, everything except for the last two sentences is irrelevant to what we're trying to do. Okay, so find the impedance of the circuit. So really, we are just looking here. And we want to take the sum of the impedances of each component of our circuit. So our power flows from this alternating current source, and then it goes through an inductor, right? We can see the coil, so we match that up in the table, which says Li. Okay, well, L is just the coefficient there. So we've got 6I. All right, and then we want the sum so that our current keeps going through. Then we get to a resistor. Notice that is just R. That's just the number. There's no imaginary component to it, so it's just 4. Okay, then we keep going, and we finally get to a capacitor, which is minus Ci. So here's this 9. That's our C value. So minus C, 9I. That's it. That's all they want us to do. Sum up those components and put i's where they need to go. And if we combine that together, we get 4 minus 3i for the impedance of that whole circuit. Very, very intimidating looking problem, but look at how little work that took to actually write out and solve that problem. So again, take the time and put an honest effort into these word problems. You'll definitely reap the rewards of that later on. All right, example 5. Now we're multiplying, and just like before, if we took a number times a number, we should end up with a number for a result. So we don't want to see anything resembling a function here. We want a nice number that's following our a plus or minus bi format, a complex number as an answer. Now, even though these are not expressions, they're numbers, we can certainly treat them as expressions. And if I were to give you this without any directions whatsoever, I would hope that you would start to FOIL them out. First times first, 7 times 8 is 56. Outside, we got minus 46i. Inside, I've got plus 40i. And last times last, I get minus 30. And there's an I times I in there, I squared. Well, the way I want my answer to be, there's no I squared in there. So we need to find a way to reconfigure that. Remember, I squared is really saying the square root of negative 1 squared. So I squared is really a negative 1. So I could think of this as 56 minus 46i plus 40i, then negative 30 times negative 1 plus 30. Now we can combine our like terms. We get 86 minus 6i. And you can see our answer, sure enough, it's following that a plus or minus bi format. That is a complex number as an answer. Number 44, we may have talked about this in class, we may not have. One of my life hacks for math. There are so many times where you need to take what looks like a binomial, a simple expression like this, and square it. You probably learned something like this in 8th grade math class, but if we have something of this form and we are squaring it, to streamline the FOILing process, again, what it's really representing is a plus b times itself. That's what squaring means. And first times first would give me a squared. Outside would be ab. Inside would be another ab. And then last times last is b squared. So I don't like to condone memorizing often, but if you can remember this simple pattern, it will make you a much, much more efficient math student. You don't have to, but it does speed things up greatly. So let's try that here in this example. And if you latch onto it, excellent. But if you don't worry, you can always FOIL this out. Just remember that we need to do the FOIL method here. So 8 minus 3i, that quantity squared, I do first thing squared. 2 times the first times the second, 2 times 8 times negative 3i, 16 times negative 3i, that's negative 48i. And then the last thing squared, negative 3 squared is positive 9, and we got to square the I as well. Now remember, this I squared is meaning negative 1, so instead of plus 9i squared, it's actually minus 9 when we simplify that I squared. So I end up with 55 minus 48i for my final answer. And that's what we should expect, right? We're taking a number and squaring it. We should end up with another complex number. All right, example 6, solve the equation. So we talked about in chapter 2 several different equation solving techniques, or maybe it was just section 3.1 actually that we went through that. We've got factoring, we've got the square root method. But here you can see number 50, we got x squared plus 49 equals 0. I've got my variable squared, there's no other x terms, so I don't need to factor. Let's isolate that x squared. And then we can solve by square rooting both sides. Okay, now we're taking the square root as a step in problem solving, so that's plus or minus. And then square root of negative 49 is like square root of negative 1 times square root of 49. Square root of negative 1 is I, square root of 49 is 7. So my solution is plus or minus 7i. All right, now you don't have to go through all of these steps. This is just to illustrate the thought process that should be occurring in your head. But I know right away that many of you will be able to set this up and come up with your solution pretty quickly. So don't feel like you have to show all those steps every single time. All right, now we're supposed to check our solution. Well, what that means is I'm going to take 7i squared plus 49 and see if that equals 0. Test it in the original equation. Well, if I square 7, I get 49. If I square I get I squared, which is negative 1. Is that a true statement? Yes, that'll be negative 49 plus 49 equals 0. What if I did negative 7i squared? Does that one work? Well, negative 7 squared is 49, and then I squared is negative 1, so we get the same result. Good, so our answer checks out. 52, here we've got some more setup. You can see again, no x terms, so we are good to use the square root method. Let's add 9 to both sides. And then we're good to square root both sides. So x equals plus or minus square root of negative 6, which is root negative 1 times root 6. So x equals plus or minus I root 6. Okay, that's the solution we arrived at. We cannot simplify the 6 if we wanted to try a factor tree. You can see no pairs are made up when we divide that radicand out as much as possible, that's 6. So let's test it out. I root 6 squared minus 9, does that equal negative 15? If I square the I get negative 1. If I square the root 6, I get 6. Minus 9, does that equal negative 15? Negative 6, take away 9 more, you bet. What about negative I root 6? All right, if I square the negative I, it's like squaring a negative number. We know that's going to come out positive. So again, that's going to be I squared. Again, that will be negative 1. That's kind of tricky. Negative I is kind of an interesting thing. So negative I squared, that's really like saying negative 1 times I squared. If I square the negative 1, I get positive 1. If I square the I get I squared. So hopefully that sheds some light on why we ended up with negative 1 there. Then you can see, again, we're setting up the same equation, one that is true. Example 7, find the zeros of the function. All right, well, zeros of the function mean where does f of x equal 0? So 0 equals negative 1/5 x squared minus 10. Let's add 1/5 x squared to both sides. Then we want to isolate our squared variable, so we can use the square root solving method. Multiply both sides by 5. We'll square root both sides. So x equals plus or minus square root of negative 1 times the square root of 50. That's x equals plus or minus I root 50. And if we break down that 50, we get 25 and 2, 5 and 5. We've got a group, we've got a lone 2. So x equals 5i, plus or minus 5i root 2. We simplify that all the way. All right, here's a look at your assignment for this section.